Hi, welcome to the lesson on section 12.4, the comparison tests. In this lesson, you'll learn how to use the comparison test and the limit comparison test to determine the convergence of a series. The comparison test for series works the same as the comparison test for improper integrals. Suppose we have two series with positive terms, a sub n and b sub n. If series B converges and each term of B is greater than each corresponding term of A, then series A must also converge. In other words, if you can show that a larger series converges, then the smaller series must also converge. Along the same lines, if we can compare it to a smaller series that diverges, then the larger series must also diverge. In example 1, I'll use the comparison test to determine whether the series 1 over n squared minus 5 from n equals 3 to infinity converges or diverges. My first thought would be to compare to 1 over n squared. However, since n squared is greater than n squared minus 5, 1 over n squared is less than 1 over n squared minus 5. Comparing to a convergent series that's less than our series doesn't help us prove anything. Maybe I can try comparing to 1 over n to the 1.5 instead. By plugging in some numbers, I find that n to the 1.5 is less than n squared minus 5 for all n greater than or equal to 4. Which means that 1 over n to the 1.5 is greater than 1 over n squared minus 5 for n greater than or equal to 4. The series 1 over n to the 1.5 converges because it's a p-series with p greater than 1. So by the comparison test, 1 over n squared minus 5 also converges. Here's a suggested format for you to use when proving convergence or divergence of a series using the comparison test. First, provide a convincing argument that the series you're using in your comparison is less than or greater than the original series. If either the numerators or denominators of the two series match, then it will suffice to write an inequality showing which is greater. However, if neither the numerator or denominator of the two series matches, then you'll need to show some more work to defend the comparison. Next, state whether the compared series converges or diverges and give a reason. If you compare to a p-series, your reason can be the value of p, and then show how p compares to 1. If you compare to a geometric series, state the value of r and show how r compares to 1. If you compare to anything other than a p-series or a geometric series, you'll need to show the use of the integral test to compare. Finally, conclude with a statement of whether the series in question converges or diverges. In example 2, I don't need to use any tests to determine the convergence of this series. The series 2 to the n for n equals 1 to 100 is a finite series, so it definitely converges. The second series is geometric with an r value of 1/2, which is less than 1, so it also converges. The sum of two convergent series converges, so this series converges. In example 3, I'll try to compare this series to 1 over 2n. Since 2n is greater than the natural log of n plus n for n greater than or equal to 2. Then 1 over 2n is less than 1 over the natural log of n plus n for n greater than or equal to 2. 1 over n is the harmonic series, which is known to diverge. A constant multiple of this series will also diverge, so 1 over 2n diverges. Thus, by the comparison test, our series diverges. Another test for convergence that you may find helpful is the limit comparison test. The limit comparison test says that for two series, A and B, with positive terms, if the limit of the ratio of terms is positive and finite, then either both series converge or both series diverge. So I'll use the limit comparison test to show whether the series 1 over n to the 3 halves minus 1 half converges or diverges. Let's compare to the series 1 over n to the 3 halves. I need to calculate the limit of 1 over n to the 3 halves over 1 over n to the 3 halves minus 1 half as n goes to infinity. This limit goes to 1. Since the limit is finite and positive, either both series converge or both series diverge. 1 over n to the 3 halves is a p-series with p greater than 1, so both series converge. Now, if you didn't like the way that I used the comparison test in example 1, when we were showing convergence of 1 over n squared minus 5, you might find a limit comparison to make more sense to you here. This concludes the lesson on section 12.4, the comparison tests.